Let's talk a little bit about the difference between int and double. Every time we declare a numeric variable, we've got to decide whether we're going to create an int, which has no decimal point, or a double that has a decimal point. Now, you've never had to make this choice before probably, so you may be wondering, why exactly do we have to make the choice now? You probably remember from algebra that 2 and 2.0 are the same thing. But algebra is done with real numbers. And real numbers have this really cool property that between every two real numbers there's another one. This is called continuity, and it's totally amazing. It's one of the really special and fantastic things about that part of mathematics. But the problem is that continuity is only possible if you have an infinite number of numbers available. Well, nothing is infinite in a computer, and so we don't have real numbers and we don't have continuity. So since the numbers in programs are not continuous, we have to store the numbers using bits, because bits are all we have in a computer. Now, when I say a bit, I mean a single 0 or 1. So if we were going to use 2 bits to store integers, we would only have 4 numbers. They would be 0, which would be stored as 0, 0, 1, which would be stored as 0, 1, -1 would be stored as 1, 0. This is called 2's complement notation if you want to take a look at it online, but we're not going to cover it in this class. And 1, 1 means -2. So notice when we have only 2 bits, we have a very limited range of ints. Now, there's some real weirdness that happens as a result of that. Each int in our program is going to be allocated 32 bits, and this limits the range of integers. It limits them from about -2 billion to +2 billion. Now that's a lot of integers, and it's really not going to be a problem in most of the programs we're going to write this semester, or maybe even all of them. But it does cause trouble sometimes. So what happens if we try to store a number that's too big or too small in an int? Well, integers do something called wraparound. That is, if you add 1 to the biggest positive int, you get the smallest negative int. It actually changes signs. Now, this is a huge problem. When this happens, it's usually pretty disastrous for the program, and it's made worse by the fact that Java doesn't flag it. Java doesn't tell you that this has happened. So this is something you have to be very careful about. If we have students that are majoring in meteorology, for example, your discipline is the kind of discipline where this causes a problem. What's more, if we subtract 1 from the smallest negative int, you get the biggest positive int. So it's sort of as if the ints were in a circle, and you can be anywhere on that circle, but you can't get off it. Well, my students usually say, well, great, let's just make everything double. There's a problem with that too. The problem is that double values are not exact. For example, we can't represent 1/3 exactly. Now, you're actually familiar with that from algebra, because you can do like 0.333 and then you put a little bar over it to indicate that the 3 repeats forever. Well, we don't have anything like that available in the computer, again, because we have to use a finite number of bits, 64 in this case. Now, Java doesn't have any fractions either. All we have are decimals. Now, int values, on the other hand, are exact. There's no 1.5 or 2.5 in ints. You have 1, you have 2. So this produces some weirdness in the part of doubles too. The doubles get 64 bits, and they're stored in scientific notation. Now, the exact details of how doubles are stored are extremely complicated. You have a mantissa, just like you do in scientific notation, and then times 2 to the exponent. Now, you've probably seen 10 to the exponent before, and because that's more typical in algebra. But in computer science, because we're doing things in binary, in the bits with 0s and 1s, we tend to use 2s a lot instead of 10s. Now, what we get are about 15 decimal digits in the mantissa, but only 15. So let's think about how the numbers below would compare in programming. So they're the same number except for the last digit, but let's take a look at how many digits they have. We see that we have groups of 3 digits, and there are 1, 2, 3, 4, 5, 6 of them. So 3 times 6 is 18, and when you add in the 2 at the start, that's 19 digits. So the 3 and the 4 that are different at the end are in the 19th digit. They're not stored in the computer at all. So these values might be exactly the same in the computer. Well, that's a problem too, because losing even a little bit like that sometimes can be a big deal. Once again, meteorology majors, pay attention. What this means is that every time we do a program, we've got this critical software engineering decision we have to make. We have to choose whether it's better to have a smaller range, but have things be exact, or have a larger range and approximate. Now, this decision has a profound influence on how programs are going to work, and so we have to make it carefully. And that's why it has to be made by the programmer. That's why Java can't make it for you. Because remember, Java isn't intelligent. You are. So keep programming.